And now it's my real pleasure to introduce John Ye. John Ye is a fellow of National Institute of Standards and Technology, professor adjunct at the University of Colorado in Boulder, holding the Monroe Chair, and director of NSF Quantum Leap Institute, Quantum Sense. He completed his master's degree also with Marlon Scully. And his doctoral advisor was Nobel Prize winner John Hall. John was the last graduate student of John Hall at NIST. And when John came back to NIST as physicist and associate fellow after 2 years of prestigious Millikan postdoctoral fellowship at Caltech with the famous quantum experimentalist Jeff Kimball, John Hall donated him his lab. After 2 years at NIST, John was promoted to full fellow. John is a world-renowned pioneer and leader in the fields of quantum metrology, cold atoms and molecules, and quantum many-body physics. He is famous for building the most precise atomic clock and the most advanced quantum sensors, comparable only to LIGO interferometer. In other words, God created time, but it is John Ye who keeps it accurate for us. It's not surprising that the list of his awards and honors takes over 2 pages, including the Breakthrough Prize in Fundamental Physics, Norman Ramsey Prize of APS, Harvey Walter Award of John Physical Society, four gold medals from the US Department of Commerce, to name just a few. John is a member of National Academy of Science, fellow of APS and Optica. He published over 400 papers, which were cited over 75,000 times. His H-index is very high, at 145. For the last decade, he has permanently stayed in the list of top 1% highly cited researchers. Please help me to welcome John.
Thank you very much. Misha, you have the speaker? Good morning, everyone, and it's an incredible pleasure. Pleasure and honor to be here. Is Marlon actually in the audience? No. In any way, I don't have a direct connection to Texas A&M, except Marlon, of course. Yeah, as Olga mentioned, I'm also could consider as a student of Marlon. And so let me tell you a little bit. Actually, unlike Misha, which I did not prepare to be a general discussion, I actually did prepare the technical talk. So I apologize for that. But I hope everyone sitting in the audience will get something out of this, at least to get a sense of how amazing time we are in. In Misha's sort of closing minute, he was talking about the connection between quantum computer and quantum sensing. And I think we are scratching the surface at the moment in terms of the building these devices of atomic clocks, and now we're getting into the nuclear domain, nuclear clocks, and so on, with the quantum programmable devices involving millions of atoms. Potentially, this field will continue to go such that experimentally we can connect quantum physics and gravitational physics. It's a really amazing time that you can actually think boldly in that way. Experimentally can probe with space-time curvature when you have a quantum superposition or entanglement distributed across gravitational field. So with that in mind, I'll just give you the next 30 minutes, give you a little bit of a quick overview and what technical things we are doing. So I want to start with, and as Misha emphasized on this as well, the system size scaling. How do we unlock this amazing quantum technology? We need to build many, many atoms to maintain their quantumness so that they can work together as a quantum team to give you more and more powerful applications, whether it's computing or whether it's sensing. So let's start with one of the heroes in our field, Dave Wineland. In the late 90s, when we were graduate students, he was already demonstrating clocks based on single trapped ion And this clock is already better than the definition of the time based on cesium clock. And the field of our atomic molecular optical physics and quantum science, as you heard from Misha already, while what's going on in Texas A&M very strongly, of course, worldwide, it's a really amazing sort of a revolution is happening. And what's amazing about our field is I will list a few examples. All of those are the cutting edge of science. And 5 years later, that turned into technology that enabled the next cutting edge of science. So Dave's trapped ion gave rise to, later on, we'll hear from Chris Monroe tomorrow about trapped ion quantum computing. But meanwhile, the field of laser cooling and trapping is advancing rapidly. Misha mentioned the MOT. This is actually the magneto-optical trap developed by these pioneering figures, Steve Chu, Claude Continuigi, Bill Phillips, and so on. This technology allows you to cool atoms from thousands of Kelvin or hundreds of Kelvin down to millikelvin, microkelvin, even nanokelvin in a time scale of a second. So this is one of the world's most amazing refrigerator. You put hot atoms in there, boom, comes out 10 orders of magnitude reduction in temperature. And this technology very quickly moved on in the mid-90s, producing this amazing new state of the matter called Bose-Einstein condensation. And this was also very quickly followed by another breakthrough by Deborah Jing, who generated the so-called degenerate Fermi gas. So bosons, fermions, they can be cooled down to such amazing low temperature that you form quantum mechanical state of these atoms. And for quantum metrology, this is essentially prepared a system that has essentially zero entropy, such that you can say, what if I want to make an artificial crystal that's made out of light? I'm just going to interfere light beams to form these grids. And because it has such low entropy per particle, you'll be able to basically occupy every lattice site, if I may call it an optical lattice, every site will be occupied by one and only one atom. It's an extremely ordered system. And this immediately can see, okay, there's a bigger connection there. If Dave Weiland can have a single trapped ion and tell you a good time, what if I do this 1 million copies of that? And that should be able to allow you to build a much better clock. And this is indeed, at the turn of the century, the ideas of when I was actually working with Jeff Kimball, as Olga mentioned, at Caltech, we came up with this idea of, well, we want to trap these atoms in so-called state-independent traps, which means, I can have a clock state, G2E, and you trap them in a particular wavelength where the deformation of the trapping potential is identical for the two clock states. And Katori at the University of Tokyo had the same idea at that time and proposed the so-called optical lattice clock. And that's really the start point of building this so-called optical lattice clock, where you can form a very simple optical lattice, just shining a laser beam, interfere with a mirror, and you can form a stack of pancakes. Each one of those can contain dozens of atoms in there. And these are made out of identical fermions, because at the time of 20 years ago when we were designing the system, we want to make sure these atoms are interacting with each other very weakly, so we can make sure that you can really gain accurate time without having these atoms interacting and cause systematic errors. And you can already see, the theme of my talk is to how do you scale the system, right? We are always greedy in the sense that we want to continue to increase the performance by having more and more atoms in there. But if these atoms are interacting with each other unruly, and that could be a problem, the clock may not be accurate. And indeed, that turned out to be true when we shine the laser onto these atoms. And now you can imagine these two-level systems can be thought of as a fictitious block sphere. They're rotating. And I often hear people make analogy of qubits, quantum bits, to a little coin flip. But I want to make sure, that this coin in quantum mechanical world is not a coin, it's actually a sphere. And the states can be anywhere on the block sphere. And so these atoms, the goal is to rotate them to the so-called equatorial plane in this coherence superposition, and you just wait and see how the atom itself is rotating around the equatorial plane and eventually be able to read out what time it is. You're really relying on electrons in superposition inside atomic orbits. and to use that superposition to read out the time. But if these atoms can start to interact with each other, they will influence each other such that each little pendulum, imagine these atoms are pendulum, they are swinging back and forth, but if they are interacting with each other, then these pendulums may not be swinging all at the same rate. And this actually is the bone of this connection of quantum metrology, quantum many-body physics, and to some degree, condensed matter physics, spin models, and now quantum computer. So it's interesting, we were building clocks, and we find out by the time the precision reached the 10 to minus 17, we find all these atoms are interacting, and we have to control these individual spins. And our field is marked by this amazing experimental theory connection. And I think that I cannot underestimate the importance of Texas A&M. I think Marlon Scully, training people like Michel Lukin and so on, you can be a theorist, but you can also be experimentalist. And here I want to say, we benefited tremendously from collaborating with amazing theorists such as Peter Zoller and Anna Maria Ray, and start to build this is not just as a clock, but rather as a device to study many-body physics. And so one way to solve problems, so now I have this conflict for you. I want to put many, many atoms in the trap because I could get a better clock. On the other hand, these atoms can interact, and that will limit the coherence or limit the accuracy. So how do I solve the problem? Well, here's one solution. We actually made a clock, made the system to be extremely shallow in optical depth. Actually, we use just a few photon recoils to suspend atoms against gravity. And you still have a stack of pancakes like this. And this trapping potential is so shallow that when you can think of these atoms as individually, this is a classical picture, but in quantum mechanics, we immediately know that when the trapping potential is so shallow and is tilted by the gravitational potential, MGH, the wave function of these particles, in fact, is spread out. So you can no longer think of these atoms as localized on an individual pancake. They, in fact, are spread out. Like I'm here in this podium, but myself maybe actually upstairs and not downstairs all at the same time, right? This is one of the weird things about quantum mechanics is the wave function. And so when I drive the so-called clock transition from ground to the excited state, because I'm using the so-called magical wavelength where the potential of the ground and excited state is exactly the same. So the quantum mechanical wave function in terms of external degrees of freedom is unchanged when I go from the electronic ground state to the excited state. But because the wavelengths I'm exciting these clock transition is not commensurate with the spacing of the lattice, you can think of at this layer of a pancake, the spin is being rotated on the equatorial plane slightly differently than the spin at the upper layer and the lower layer. And what that means is that if you look at atoms in the individual layers, they are all identical fermions, and they interact with each other with a P wave. Sorry, this is a little technical term. P wave just means fermions don't like each other. They want to stay away from each other, and so their angular momentum cannot be zero, orbital angular momentum. On the other hand, the atoms in the lower layer, upper layer, you can see they are slightly different. That means they are distinguishable. They are no longer identical fermions. You no longer have a Pauli exclusion principle to protect you. They can interact with the S wave, meaning they can have a zero angular momentum for them to interact. And we can tune the relative interaction strength of the P wave versus S wave just by controlling the strength of the optical lattice. And by doing this, we can tune the S wave, P wave to be zero, such that the interaction effect is zeroed out. And this is very powerful if I show an image of the atom. This I rotated against, this atom is actually located along the gravity, but rotated by 90 degrees. They're lying horizontally. If I take a microscopic picture of the atomic distribution, the central part is more dense than on the bottom part, the other parts. And you can see if you have arbitrary trap depth, you have a huge so-called density shift, which is when you have more atoms, they have stronger interactions, and the frequency of the clock shifts away from the true value. But when I tune this Hamiltonian, quantum engineering of how the atoms interact with each other at a specific depth of the optical lattice, you can see the optical frequency shift becomes completely insensitive to the number of atoms you have per pancake. So this is the one way to tune away using this Hamiltonian engineering. It's just one trick to remove this one barrier of this conflict of, I want to use more and more atoms, but how do I make sure all these atoms are working for you in a way that you want them to be. And it's kind of interesting using this very simple concept. We can now prepare the atoms in coherent superposition. And how long can this coherence live? It can live for 2 minutes. This is actually amazing. If you think about, I put an atom in coherent superposition, the electron cloud is oscillating back and forth with a quality factor of 10 to the 17. What is that quality factor would mean? If I had to slow down this electronic oscillation by 10 to the 15 times and look like your grandfather's pendulum, 10 to the 17 would mean if somebody put their pendulum clock at the beginning of the universe, at the Big Bang, that pendulum is still swinging today. That's how good this quality factor is. So with this, obviously, we can start to explore some very fundamental physics questions. Everybody have heard about Einstein's general relativity. We all know if you move clock to the satellites, time is different. If you move faster than your colleagues, you get to live longer. Things like that. The time is all relevant. And so what's amazing now is imagine this is actually a picture of our atomic cloud spanning a few hundred microns. And if the atoms live a little bit closer to the Earth versus the atom that's living a little further above the Earth, they actually tick differently. And we know this, called Einstein's general relativity time dilation effect, gravitational time dilation, or the other way called it redshift. But we cannot explore this over just a few hundred microns, meaning if you have your watch, take it off your wrist, move up by 1 human hair width, that watch should, in principle, tell you a different time. And this is what we're measuring. These atomic clocks now can measure gravitational redshift at a 100 micron scale. What if you keep going? As we forward looking, what if so I apologize for the Hamiltonian. It's a first ever Texas Quantum Summit. I know there's a lot of geeks and a lot of nerds here. And so some of you may like this. I'm writing this Hamiltonian just to describe how the atoms interacting within the same site, on the same pancake, or they're interacting off the pancake. And there's one more term of Hamiltonian people usually don't write because that term is usually very tiny. That's the so-called general relativity term, the gravitational redshift. Because general relativity describes macroscopic physics, large celestial bodies. Quantum mechanics describe very microscopic physics, atoms, photons. Well, wouldn't it be amazing that on the quantum scale, you start to see general relativity effects? And this is kind of pointing to that direction. If I have a gravity, and I have atoms like this, and you have this GR, general relativity term of the Hamiltonian, which tells you each pancake, the time is evolving differently. And imagine you put an atom in superposition, in coherent superposition of a wave function, but time here and time there is evolving differently. Well, that quantum state cannot survive if the time is twisting. And that's interesting. We can dream about these things, but maybe in the next 5, 10 years, we can start to explore these. How gravitational physics gets to interplay with quantum mechanics. So in order to do that, and now I'm going to the topic of entanglement that Michel Lukin was talking about. So I showed this block sphere already, and I put atoms in coherent superposition between ground and excited state. The energy difference between the excited ground state evolves as a phase, ET, and indeed, I measure this little phase, and because I know the energy so well, this will tell me the time. This is exactly the basic principle of atomic clock. And you can immediately see, because atom is in coherent superposition of ground excited state, that coherent superposition is not eigenstate of the Hamiltonian. Only ground state, excited states are. And so that means when you make a measurement, there will be a quantum uncertainty. And this is represented by this fuzzy ball, indicating my phase is actually limited by the quantumness of that superposition. And this is the fundamental limit. And the way to overcome that fundamental limit is exactly what I just discussed earlier. You use lots of atoms, because by averaging away that white noise, you can remove that noise. You can get the phase sensitivity to be better and better, the so-called standard quantum limit in the classical case where you have many, many identical atoms measuring together. You can actually scale the precision is 1 over square root of how many atoms you have. That's the power of the large N. But what if you can actually have entanglement? Which means, what if every atom's quantum noise become correlated? Okay, this is the same thing that Misha is doing on quantum computer, correlating those noises. For me, the quantum noise is what's limiting my clock precision. If I can have all the noise to be correlated, that means maybe I only have one copy of noise, but I still have n copy of signal. So now the phase sensitivity scales is 1 over n instead of 1 over square root of n. Well, that would be amazing enhancement. This is what the quantum entanglement will coming in to help in metrology. Unfortunately, as we all know, entanglement is rather fragile. So now how do we play the game of scaling the system up? And I want to just show you a couple examples now. A spin-squeezed clock. And what do I mean by spin-squeeze? This is superposition in the classical quantum mechanics. We talk about individual particles. Wouldn't it be amazing if I can somehow redistribute the quantum noise into a little bit like a cigar-looking thing? And that means when the cigar is moving around the equator, well, I will have a better resolution to see where the cigar is because cigar looks thinner than a sphere. So how can I do that? By doing quantum entanglement to give myself more sensitivity to the phase. And we can do this, and actually this is the same Vladan that Misha has been collaborating. So Vladan came up with one idea, which was, what if I put atoms in between two highly reflecting mirrors? And this is actually the trick also I learned at Caltech with my PhD advisor, postdoc advisor, Jeff Kimball, who is a Texan. He was incredibly proud to be a Texan. He always tells me, the best beer is in Texas. He's a vegetarian. He talks about steaks too. But Jeff is a true amazing pioneer of cavity QED. Unfortunately, he's no longer with us. He retired to Austin, Texas, but passed away last year. But Vladan has taken up on that work, basically saying, if I put atoms in between these two highly reflecting mirrors, such that when the photons are running back and forth between the pair of mirrors, I've got thousands of atoms inside that cavity, but I cannot tell which atom is interacting with the photon. And the universe cannot tell which atom has interacted with the photon. And that fact alone, Feynman would tell us, that fact alone, you can actually create entanglement, create correlations of the atoms. And this is what we do. We put an atom in superposition between ground and excited state. This is my clock states, remember, G and E. And I put these atoms are in the lattice, which can be thought of as a little elevator. I can move the atoms into this highly reflecting cavity in the sample A, and then can move them out, put a sample B inside. I can then compare two clocks, A and B, to measure gravitational redshifts. What a cavity is doing is, you can think of as a little spy, because Misha mentioned the quantum physics is extremely fragile. You cannot clone that information, right? So this is the hardness of the quantum, is that your prepared superposition is extremely fragile. You're not supposed to be looking at it. But the noise is, in fact, in that superposition. So what if I can somehow come up with a technique, so-called cavity QED? I want to insist on getting more information of how many atoms, where I prepare superposition from ground excited state. I want to spy on how many atoms are actually in the G state. Okay, that question sounds like you should never be able to do that, except in this particular case when you have thousands or hundreds of thousands of atoms in between a single mode of cavity, when the photon cannot distinguish which atoms are interacting, you actually can do that. This is the so-called QND measurement, and pioneered by another Nobel laureate, Serge Haroche. And so now you can see where the protocol is. I prepare atoms in superposition, traditional coherent superposition, and I turn on the little spy field, and I can now squash down because I gain the information of whether atoms in the ground or excited state. So my distribution of noise gets a little thinner. And then all I need to do is to rotate these qubits by 90 degrees and let them evolve. And this is a little thin cigar running around the equatorial plane will give me better phase sensitivity. And so this is like the first, in fact, almost state-of-the-art clocks that enjoy a couple dBs of gain due to this quantum entanglement. But to be honest, This is at the level that's not quite at the level of 10 to minus 20 that I was telling you about. So let's talk about this really quick, since this theme of my talk was how do you scale quantum systems. The single clock instability that we're very proud of using spin squeezing reached 1 times 10 to minus 15 at a second. This number, if we 5 to 10 years ago, would be an amazing number. But it's no longer, because we have been making progress with unentangled clocks, now reaching at 1 times 10 to minus 18 at a second, meaning if you wait a second, you can already measure time at the level of 10 to minus 18. Okay, and so you can see there's a 3 orders magnitude. The question really is come down to, and it's not just us, this is Valadin's work. In fact, his clock is at 10 to minus 12, 10 to minus 13, but he was doing the demonstration, trying to show the principle of physics works. This is actually the work recently with my colleague Adam Kaufman in Jilla, using very similar the atom tweezer array, using Riedeberg squeeze, the interactions to generate spin squeezing. And you can see very similar to this results, a few parts 10 to the 15 at a second. So the entanglement is showing the advantage, but not at the state of the art. How do we push that? Well, it turns out we need to really generate a spin squeeze state with very many atoms, larger number of samples, and the entanglement must be long-lived. In Valadin's experiments, for example, his entanglement lived only for a millisecond, and that's not useful. So can we push entanglement to a much longer time, and so on. So I know one example, there are many tricks we have to do in the lab to push this kind of a field forward, but one of the things that I want to share with you really quick for people who in the audience who are very technically oriented, I have this cavity probe, which is a spine field I was telling you about, and it's just like a LIGO, the gravitational wave detector. You need to give enough photons to be able to sense the information. LIGO is famous for this, right? You have 2 mirrors, and the gravitational wave hits it. The two mirrors start to swing. How do I measure how much gravitational wave has hit my mirrors? Or you have to measure the length by doing interferometry. In order to measure the length well, you have to put a lot of photons in there. But when you put the photons in there, photon carries a pressure. It will have a back action. So this is the pros and the cons. You get a more and more greedy on signal, but I still have time, right, Olga, right? Only a minute. Oh, I thought I still have 5 minutes. Anyway, I will try to be quick then. So this with more photons, you will hit a technical noise floor. But when you have too many photons, you're going to have issues of AC stock shift. So what we are playing tricks is putting in 2 different optical fields in there to cancel. If I'm having 2 cavity modes, which are 2 free spectral range apart, the 2 standing waves are opposite in phase. And you can control such that the phase AC stock shift, one is a red detuned, one is a blue detuned, cancels each other, such that we can cancel this quantum back action by the AC stock shift on the probe. This is just one trick among many to allow you to be able to really do spin squeezing better. And in fact, just this year, we were now able to show the spin squeeze clock can work at a 10 to minus 18 level now after 3,000 seconds. This represents a 20 times improvement just by play tricks like this. And I think there's many more rooms to improve. And in fact, I would say we are now relatively confident in the near term, the spin squeeze clock will be able to catch up with the best state-of-the-art precision of the clocks. I want to touch on nuclear clock really quick. Is that okay? Yeah, just 1 minute. Well, I was supposed to have 30 minutes, and right now it's 26. Okay, sorry. I should be respectful. It's a capital crime. I promise 1 minute. And the 1 minute is just to show you this. We have another way to scaling up, but I want to just get to the point of the nuclear clock. You put more and more atoms in there. The atoms can interact. This is the theme I've been telling you about. But what if we can go back to the old days of a mass power spectroscopy and actually discuss the nuclear clocks where atomic physics actually borrowed a lot from nuclear physics, whether we do ion clock or lattice clock, it's all about recoil-free systems. But if we can turn the incoherent mass power spectroscopy into laser-based coherent mass power spectroscopy, the world will change. And so this is basically in, Olga, this is your work, so that's why I want to borrow that 1 minute. You know, this is a nuclear clock idea that there's a thorium-229 happens to be at this region where the lifetime is actually 20 minutes, and a 10 eV, we can actually access it with the current laser technology. Maybe there's another transition in uranium, and in fact, August's collaboration here that I cited here has a scandium at a 10K eV, and if we can really have coherent light source to be able to drive these nuclear transitions, the whole field of nuclear physics completely changes, right? Just like when we invented the lasers to drive atomic transitions, atomic physics is no longer the same. And so let's see if, and I don't have time to show you, except to tell you that indeed we can now generate this coherent light source in the VOV, and we can start to drive these nuclear transitions like this directly in optical domain, and actually even show they can be coherently connected between atomic clock and the nuclear clock. And over the past 6 months or so, we are already showing the frequency is stable to within 200 hertz. And that's limited by the measurement precision, not limited by anything that we are seeing as a problem. So with that, I hope you can see the quantum system scaling continue to advance. And we don't have to even stop at atomic physics. We can really go to even other areas of physics where quantum is going to have a major impact on the fundamental science. So with that, I want to end here with this slide, just to make a historical connection to where people use the mass power spectroscopy in Harvard to measure the redshift, and we can now measure the redshift here. And now the two fields of mass power spectroscopy, atomic clock, is united. Thank you very much.
Thank you, John.